Hello, this video covers the topics related to Lab 1, which are MATLAB environment, functions, matrices, and plotting. This is a summary of what we're going to discuss throughout this video. First, we'll talk about what MATLAB is, and then we'll introduce MATLAB environment and workspace, variables, operators, built-in functions, matrix manipulation, generating plots in MATLAB, subplots, and then finally we'll talk about some other useful commands in MATLAB. First of all, what is MATLAB? Here you see the logo that some of you may be already familiar with, which is the software logo. MATLAB actually stands for two words, matrix laboratory. It is a sophisticated mathematical computational tool. You can say that it is a complex yet easy to use calculator, and it is very widely used in many fields, especially in signal processing. And a very important note on MATLAB code, MATLAB is case sensitive, meaning a lowercase variable differs from an uppercase variable. Now, this is a screenshot of what MATLAB looks like. Here we're going to highlight some of the important parts of the software. And here you see the buttons or the icons needed to create, save, or open a script file. And this is where you have the current folder. You will see a list of all the files you've created and saved in the project or in that current folder. You can double click a file to open it, or you can go to file open, or actually click on the open button to open a file. And in here you see the working directory. Currently I'm working in the MATLAB folder itself, and this window is containing all the code that I'm currently writing in the file project1.m. So this is the MATLAB script file. And notice that the file format or the file type for MATLAB is .m. And in here you see the button you need to use to run the script file. So any code that you write in the script file that you want to run or compile, you can simply click run, and in the command window you'll see the output. For example, here this is a simple code that computes 3 times 4 by first assigning A a value of 3, then assigning B a value of 4, then evaluating Y to be equal to A times B, and the result is outputted in the command window as 12. Here you see the workspace in which you will look at all the current variables that you have along with their values. Now we'll discuss MATLAB's built-in variables. In MATLAB, there's already some built-in variables that can be accessed easily, including the pi, which we know that has a value equals to approximately 3.14. Another built-in variable is the epsilon. We also have I and j, which are the imaginary number, square root of -1. Notice that some variable names in MATLAB can be reassigned a value. For example, I can say simply I is equal to 2 and then reuse I, so it will have the value that I assigned myself rather than the built-in, the default value, which is the square root of -1. Another very special built-in variable in MATLAB is ans, which is the answer, short for answer, and that variable always stores the most recent computation result. For example, here I typed in MATLAB EPS, short for epsilon, and MATLAB will automatically print out the value of epsilon, and the built-in variable answer appears in the workspace, and it will have the value of 2.2 times 10 to the negative 16. In MATLAB, you can also have user-defined variables, and variable names must start with a letter, and they may contain numbers or an underscore. There are different types of variables, including a scalar, an array, or a matrix. Here, for example, A is assigned a value equals to 2. It's just a scalar that's equal to 2. T here is an array starting at 0, incrementing by 0.5 until it reaches 3. A is a matrix of size 2 by 2, meaning it has 2 rows and 2 columns, and its elements are 1, 2, 3, and 4. In MATLAB, if you add a semicolon at the end of a line, it means the output is suppressed, meaning you won't see the output in the command window. But if a variable is being assigned a value, then its value will be updated, but you won't see that result in the command window. For example, here we have assigned a value equals to 2, and A will be created in the workspace, and it will have a value of 2, but you won't see 2 being outputted in the command window. To create arrays in MATLAB, you can either separate elements using a comma and list them one by one, or you can use the shortcut of the colon as such. So first you will put the variable name, t for example, and then the equal sign, and then start with the initial value 0, put a colon, and then in between you're going to put the incrementing value. Here it is 0.5, and then another colon, and then the limit value, which is 3. So in English, here we can say that t is equal to an array starting at 0, incrementing by 0.5 until it reaches 3. Another way to create an evenly spaced array in MATLAB is to use the linspace function. So linspace is short for linearly spaced points. So in English, we can read the last line of code here as x is equal to an array of evenly spaced points or linearly spaced points between 0 and 3. And we have a total of 7 elements. Another way to put it is to say that x is an array containing 7 elements starting at 0 until less than or equal to 3. So 3 is our limit here. Notice that x and t are equal and they're equivalent, and we've used different methods to create them. Now we'll discuss some of the common operators in MATLAB. We have mathematical operators, including addition, subtraction, multiplication, division, and the power operator. We have array operators. Array operators are mathematical operators that applies to arrays or matrices in general. You can simply put the multiplication operator along with a dot that precedes it. We'll explain the difference between the two later on. We also have the comparison operators, such as the equal, which will check if two variables are equal. We have the not equal, which consists of the tilde, then the equal sign, greater than or equal to, and less than, and so on. We also have, finally, the transpose operator, which will output the transpose of a matrix. For example, if you input a 2 by 1 matrix and apply the transpose operator on it, you'll end up with a 1 by 2 matrix, and so on. Here we can say that A is assigned an array with values starting at 1, ending at 5. Here we only used one colon, since in MATLAB, by default, the increment value is 1 if you only use one column. If you want an increment value different from 1, you're gonna have to use 2 columns and put the increment value in the middle, just like what we did in one of the previous slides. Here we've created another array, b, which is equal to a plus 2. So we'll find out that b is simply similar to a, except we have 2 added to each element. Then we typed a dot multiplication b. So this is an array operator that multiplies each element in a with its corresponding element in b. The first element in a is 1, first element in b is 3, so a dot times b is equal to 3, or the first element in that array is 3, and so on. Here we're assigning a value for x equals to 4, and then we're saying that y is equal to 2 times 2, and then finally we're checking using the comparison operators if x is equal to y. And then the output is a logical 1 because the statement is true. Now we're going to examine a simple example on operators. First, we have an array consisting of angles and degrees. We named the array degrees. And then our aim is to convert the angles from degrees to radians. So we can create a new variable named radians that's equal to degrees multiplied by pi, which is the built-in variable, 3.14, and then divided by 180. Since we did not put a semicolon at the end of the line of code, MATLAB will output the result for us. So the result would be the values in radians of the inputted angles. Finally, we can place the two results in 2 separate columns by applying the transpose operator and using the square bracket to generate a new matrix. So the conversion table is equal to a new matrix or array whose first set of elements includes the degrees transpose. So we'll convert the degrees array from a row vector into a column vector. We'll also do the same for the radians vector. We're going to convert it from a row vector to a column vector as such. Another way to evaluate the conversion table is to place the degrees array first and then use the semicolon. The semicolon will simply create a new row in the matrix, and then in the new row we're going to put the second array, which is the radians, and then after we evaluate the entire matrix we're going to apply the transpose operator to it. Try to examine this script file on your own desktop to experiment with it further. Now we're going to move on to built-in functions in MATLAB. There are various built-in functions in MATLAB that are available. Some of the commonly used ones are the square root of any number, the sine, the cosine, the tan, min, max, and so on. There are functions in MATLAB that have more than one output, such as the size. The size will output how many rows and how many columns in a given matrix. There are functions that require one or more inputs, such as the zeros function. Here we're creating a new variable named x, whose value is equal to sine of pi over 2. Notice we've used a semicolon because we don't want to read the output, we just want to store it in x. And then in the next line of code, we're evaluating the square root of x divided by 2. So after we've evaluated x, we applied another function, which is the square root, on x divided by 2 to compute the square root of 1 over x. Next, we have a function that requires more than one input, which is the zeros. It will create a matrix consisting of zeros for the given size. The size we give it is 1 by 3 or 1 comma 3, meaning we want a matrix consists of zeros that has only one row and 3 columns. Now we can call the size function on A. Since size will output more than one output, we can simply store the output of size of A into an array of variables. The first element in the array is rows, and then we have columns. So since A has the size 1 by 3, meaning the number of rows in A is 1 and the number of columns in A is 3. Here's an example of a function that can take one input or two depending on the application. Here we've initialized a matrix named x of size 2 by 3, meaning it has 2 rows and 3 columns. And then we called min_x. Min_x will output the minimum value in each column. So the output of min_x is actually a row vector consisting of the minimum element from each column in x. Calling min function with 3 arguments, the first one is x, then an empty matrix, and finally 2, will output a column vector containing the minimum element from each row in x. Now we're going to examine some other built-in functions in MATLAB, including find, sort, sum, and ups. First, we're initializing an array named y that consists of 5 different integers. The function find y will output the indices of the non-zero elements in y. Notice that the first index in MATLAB starts at 1. Since y consists of a 0 in it, there's a 0 in it, meaning find y will ignore the third element, or it will not output the index 3, but rather it will output all other indices, including 1, 2, 4, and 5, since these correspond to non-zero elements in y. The function sort by default should output the sorted version of its input, but since here we are passing a second argument, which is the text descending, meaning we're interested in sorting y in descending order. So sort y descending will output the sorted version of y in descending order. The function sum y, from its name, will simply add the elements of y and output them in the command window, or store them if you are assigning the result to a variable. Function apps y will result in taking the magnitude of each element in y and then outputting it to either the command window or to a variable. In MATLAB, it is allowed to nest functions. For example, here we have an array named k that starts at 1, increments by the default value of 1 until it reaches 5, and then we're calling the function sine and the function square root on 1 over k. Notice that here we're applying the array operator, the array division operator, meaning we want to take the reciprocate of each element in k. So we're not dealing with k as a matrix, but we're dealing with it as individual elements. So square root of 1 divided by each element in k is taken. Then the output of that goes to an input for the sine function, and then the result, we applied the transpose operator to it. That's why the answer or the result is a column vector, whereas k is actually a row vector. And the reason why we have it as a column is because of applying the transpose operator. Now we're going to learn how to deal with matrices in MATLAB, starting with how to create a matrix. To create a matrix in MATLAB, we need to place the elements or the values of the matrix between square brackets. You can either store the output to a variable or simply output it to the command window. Here we're initializing a variable named m to have a matrix stored in it that consists of 2 rows and 3 columns. You can separate elements within the same row using either a space or a comma as such. Notice that elements 1, 4, and 5 are in the same row. That's why we've separated them using a space. A comma would work as well. And then to separate rows from each other in a matrix, we need to either place the values in a new line of code or to use a semicolon like we did here at the beginning. Here, X is also a matrix, but we used the shortcut of the colon operator to create the first row as well as the second row. So the first row in X consists of 1 through 5, incremented by 1. The second row in X consists of 6 through 10, incremented by 1. Notice that we've used the semicolon in between the two arrays to indicate that we're transitioning to a new row. Now we're going to deal with matrix manipulation, 1D matrices, and how to extract elements or edit them within an array. Notice that, as mentioned before, indices in MATLAB start at 1. So, for example, if we type x1, this will output the first element in x, which is -10 in this example. If we type xend, it means we want to find or output the value in the last element in x. So xend will output the last element in x, which is 0 in this example. X4 will output the fourth element in x, but here what we're doing is actually we're assigning the fourth element in x a value equals to 66. So this will result in updating the array x by changing the fourth element in it to 66. Alternatively, if we type x of 8 is equal to a number, notice that x does not have an element at index 8. So index 8 does not exist in x. So if we say x8 is equal to 9, for example, What MATLAB will do is that it will change the size of x such that it will have an element at index 8 equals to 9, but any non-existing values in between will be assigned a value equals to 0, as we see here in this example. Now we're going to examine how to extract and edit elements within a 2D matrix. For a 2D matrix A, for example, calling AR, C will output the element that's located at the intersection between the rth row and the cth column in A. AR, colon will output the rth row in A. Alternatively, A colon, C will output the cth column in A. If, for example, we type A1, colon, that will output the first row in A as we see in this example. We learned in a previous slide that end means the last index. So typing A and colon will output the last row in A. Calling AR colon equals to 0 will adjust the matrix to A such that it will assign zeros to all the elements lying in the rth row of A. Here, finally, calling AR, C equals to B will adjust the matrix A such that the element lying at the intersection of the rth row and the cth column will be assigned a value equals to B as we see in the example here. For a 2D matrix, if we type A colon, this will output all the elements in A in a form of one single column. For example, here A consists of a 2 by 2 matrix. Typing A colon will output a column consisting of 4 elements, which are the 4 elements in A, 2, 1, 3, and 4. Typing B colon 1 through 2, for example, will output a range of columns in A, starting with the first column until the second column. So in this example here, we see that the first 2 columns in B are outputted, and the third column is being ignored. Now we're going to study matrix arithmetic in MATLAB. Since MATLAB stands for Matrix Lab, it makes sense that the multiplier operator, if used between 2 matrix variables, it will output the result of multiplying these 2 matrices. For example, A times B or A asterisk B will output the matrix multiplication of A times B. However, if we use the array multiplication, which is the element-wise multiplication, by putting a dot prior to the multiplication operator, this will output the result of multiplying each element in A with its corresponding element in B. Here we're using A dot multiplication A as an example. Notice that A is of size 2 by 2, so matrix multiplication here is possible, but instead what we intend to do is to multiply each element in A with itself. So that's why we used the array operator or the element-wise operation. So A dot multiplication A, we can say that it is equivalent to A dot power 2, meaning each element in A is being squared is equivalent to multiply each element in A with its corresponding element, or with itself basically. Now we're going to discuss Some particular functions in MATLAB and how to apply them on arrays. Here we have an example of a variable named x that stores in it a 1D array whose elements are -10, 4, 3, -2, and 1. Calling the function minx will result in finding or outputting the smallest value in the array x, which is -10 for this example. The function sumx will output the summation or the addition of the elements in x, which results in the output being -4. Calling sort on x will output the sorted version of x in ascending order, which is the default order. If we are interested in sorting x descendingly or in a descending order, we need to use or pass an additional input to the function sort, which has the text descending. There are other functions such as the standard deviation, which is std. We also have the function mean that finds the average of the elements in an array. There are various other functions that can be used on arrays. For example, if we call the sign function on the array x, the output will result in an array of the same size as x, but the values of the output would be the sign of each element in x. Another function that can be used with 1D arrays is the find function. Function find outputs the elements or the indices actually of the non-zero elements in an array. You have to know that the first index in MATLAB is 1. So the second element in an array has an index equals to 2 and so on. First, we can initialize two arrays, x and y, to denote x and y as a function of x. So x is the independent variable, y of x is the dependent variable. But in MATLAB, to initialize a function as y of x or a signal, we can simply state it as y is equal to the array such and such. We cannot simply say y bracket x because this is the mathematical expression rather than MATLAB code. So calling find x in this case, as we said, is going to output the non-zero indices in the indices of the non-zero elements in x, which are going to be the second element, the third element, fourth element, fifth, and sixth. Notice that the first element in x is 0. That's why index number 1, or the first element whose index is 1, is not appearing. The index of it is not appearing as one of the outputs for find x. If we apply the comparative operator on an array, the result would be comparing each element in that array. Here we have an example that's saying, is y equal to 9? So we're checking if y is equal to 9. Remember, if you put double equal signs, it means you're comparing. So this is the comparative operator. It's not assigning a value of 9 to y, but rather checking whether each element in y is equal to 9. Since only one of the elements in y is equal to 9, and that is the third element, then y equal 9 outputs an array whose elements are all zeros except for the third element, because the third element in y is actually equal to 9. Calling the code x find y equal 9 will result in finding the x value that will result in y of x being equal to 9. Notice that you can pass an index to extract an element from an array, or you can pass a logical value. So using find, the function find as such here will result in finding the value of x that will result in y of x is equal to 9. differently put, we can say that when x is 3, when x is equal to 3, y is equal to 9, or y of 3 is equal to 9. Differently put, you can also write this MATLAB code using simply x, extract the element in x, for which y of x is equal to 9. This is how we state that in MATLAB. Notice that here we're assuming y is a function of x. So when x is equal to 3, y is equal to 9. And here we're trying to find the value of x that will result in y being equal to 9. But notice that since y is the dependent variable and x is the independent variable, so this is actually a combination of x and y of x, it means we need a pair of x points and y points. So that indicates that y and x must have the same length. Now we're gonna learn how the functions min and max react or work on 2D matrices. Assume we have a matrix of size 2 by 3 named x, meaning it has 2 rows and 3 columns. Calling min x on that matrix will output the smallest value from each column in x, meaning the result would be a row vector containing the smallest element in each column of x. Another way to reach or accomplish this output is to call the command min x empty matrix 1 to find the minimum value from each row in x, meaning to output a column vector containing the smallest value in each row in x. We need to call the command min x empty matrix 2, meaning we want to find the minimum value from the second dimension in x. Here we have a tip that combines some of the commands we've learned so far. So if we're interested to find the smallest, or actually the maximum, for example, value in the nth row of x, we can simply call the command max x n comma colon. Notice that the input here for max is actually the nth row in x. So it's a 1D array, and we're trying to find the maximum value in that 1D array. Now we're going to learn how to apply the sort function on 2D matrices, or what it will actually output. First of all, by default, as we mentioned, MATLAB sorts in ascending order. So for example, for matrix x, calling sort x will sort each column in x, and the result would be this matrix here. Calling sort x comma 2 will sort each row in x, again in ascending order. So this means in English, sort x according to dimension 2, the second dimension. Calling sort rows, this is a different function named sort rows, on x, it will sort the rows of x according to the first column by default. So if we want to find or if we want to sort the rows of x according to a different column, we need to specify that column. Remember, or notice that the function sort does not alter the input. So the output of this, or the results of calling any of these functions, is not going to affect x itself, but rather it will just output the sorted version of x. So if we want to use that output, we need to store it somewhere. If you want to update x, you need to simply say x is equal to sort x, for example. If we're interested in sorting a matrix in descending order, we can benefit from what we've learned, but we need to specify the order. So we can say sort x, comma, text stating we want to sort each column in x in descending order as such. If we want to sort each row in X in descending order, we need to say sort X, comma 2, comma descending. In English, this means sort along the second dimension in descending order. The function sort rows X, comma descending will sort each row in X based on the first column by default. So if we want to sort the rows of a matrix in descending order based on another column instead of the first column, we can simply put the column number with a negative sign in front of it. So for example, here we have sort rows X, comma negative 4, meaning we want to sort the rows of X according to the fourth column in descending order. Now we're going to move on to learn how to plot using MATLAB. The first method we're going to use is to plot a graph using the plot function. First, we need to initialize the variables that we're going to plot. Assuming here that we have a variable named x, this is the independent variable that starts at 0, increments by pi over 100 until it reaches 2 pi. The functions that we want to plot, or the signals, are y of x and f of x, but in MATLAB this translates to simply y and f separately. We can add a comment stating that this is actually y of x, or y is a function of x, but in MATLAB we cannot say y bracket x for this particular case, but rather you can simply say y is equal to sine of x. So x and y will have the same length, but x is as we defined it, y is going to be sine of each element in x. The function f of x is defined as cosine of x, and then here we are typing figure to open a new figure window in MATLAB. The next step is to call the command or the function plot on x, comma y. So notice that we always put the independent variable first. So if we want to plot y of x, we're going to put x, comma y. If you simply put plot y, it will work, but it will not put the x-axis, the correct x-axis values in there. So we need to specify what is the independent and what is the dependent variable is. Next, we type hold on, because in this example we're plotting two different functions on the same graph. So the keyword hold on will hold on the current graph and wait for the next plotting command so that the two plots will be plotted on top of each other. So once we're done with all the plots, you can plot more than one graph at once, or I mean on the same figure window. But once done, you need to type hold off. For the second plot, we're choosing to plot it using a different style, which is a dashed line. And to do that, you need to add an additional argument and pass it to the plot function. So this is specifying that now we want to plot f of x. Notice again, we put the independent variable first, x, and then the dependent variable, and then the style if necessary. Next, we are simply adding a title for our plot. Notice that the title is meaningful and it's descriptive. It describes what you see in the figure. Then the x label is the independent variable x. The y label is non-existent. Here in this case we did not put a y label, but rather we put a legend because we have two plots superimposed on top of each other. So we need to indicate using a legend what each color or what each plot is actually for. Another plotting function in MATLAB is the bar function, which will draw a bar graph for us. Here we have an example in which we're interested in creating a bar graph that will help us compare the standard deviation and the mean of two scores sets. The first scores set is named scores1, and then in the second array here we have a variable named scores2 that will store the second list of scores, and we first need to create an array that stores in it the standard deviation values for each scores arrays. So the variable name is deviation, and it consists of two elements. The first element in it is the standard deviation of the first scores array, and the second element, which is located in the second row since we've used a colon or a semicolon actually, will store in it the standard deviation of the second scores array. Next, we need to evaluate the averages of the two scores sets. So we're creating a variable named average that has two elements. The first element calculates the mean of the first array, so mean scores1, and we put here a semicolon, which means we need to move to the next row, and then the next element in average is the average or the mean of the second scores set or the second scores array. So both deviation and average are actually column vectors that consist of two elements, so they're both a 2x1 matrix. Next, we're creating a table or a matrix named stat that concatenates or combines the standard deviation of both scores sets, and in the next column it has the averages of these two scores. Next, we're opening a new figure window by typing figure and then call the function bar by passing the stat matrix or table as an argument. Finally, we need to add a legend to explain which color corresponds to what. But make sure that you always put the legend text in the same order as the table itself. So the deviation variable comes first, that's why the first label is the standard deviation, and so on. Finally, we're adding a meaningful title, which is scores statistics, for example. The third function that we'll learn to plot within MATLAB is mesh. Mesh basically creates a 3D mesh plot, but first, in order to be able to use it, we need to use the mesh grid function. So first, we need to initialize the x-axis values and the y-axis values, and then call the function mesh grid that will create the 2D grid coordinates for us based on the coordinates obtained from x and y. Then using the matrices x, uppercase x and uppercase y, we can generate or evaluate the value of the values of the elements in Z. So we'll use uppercase x and uppercase y that are outputted by the mesh grid function to evaluate uppercase Z, which we're going to plot using the mesh function. Next, we're typing figure to open a new figure window as such, and then we're calling the function mesh on x, y, and z. Notice mesh helps us create a 3D plot. That's why we need to pass for it 3 variables: the x, the y, and the z matrix. Finally, we're adding a title and labels for our graph. The last plotting function we're covering is the function contour. Contour creates a contour plot of a matrix Z in the xy plane, meaning it will need 3 variables, x, y, and z. Thus, we'll first use the mesh grid function, the same way we did with creating mesh plots. Next, we can simply call the function contour by passing the variables x, y, and z as arguments. Then we can add a title and labels. Notice here we did not need to add a z label because we only need the xy plane, and then the levels that are appearing here, or the contours, are there to correspond for the z value or the z-axis. In order to be able to plot specific levels, so not all the z's but specific values for z, we need to create an array named, for example, v, in which we're going to list the levels we're interested in looking at. In this example, we want to look at levels 3 and 5. So what we're going to do is create an array named v, for example, and store in it two elements, 3 and 5. Then we're going to pass an additional argument for the function contour that includes two copies of v, so a bracket, square bracket, v space v, and then we're going to put a comma, show text, just for us to have a label on each of the contours that are drawn. So notice here that we have plotted two levels, level 3 and 5. 5 is shown in yellow and it has a label on it, 5, it says 5. And level 3, so z is equal to 3, is colored in purple. Finally, we can add a title as well as labels. So as mentioned here, this setting is optional. You can add it or omit it. You can choose to show text, so we need to say show text in this exact spelling, and then comma on. So this will adjust the settings of the contour plot so that it will display the level values on top of the figure. Now we're going to move on to using subplots in MATLAB. So the function or the command subplot rcn simply creates an empty grid consisting of I rows, C columns, and then it will wait for the next plotting command that you will type either in the command window or in the script file itself. So the last argument in subplot is actually the location of the next plot. Here we have an example in which we have two functions, f and y, and they're both a function of t, so f of t and y of t. T is initialized as an array starting at -10, incrementing by the default value 1 until it reaches 10. Y is f of t is t squared, so each element in t is being squared. Y is equal to t raised to the power 3. Then we type figure to open a new figure window. So the command subplot 1, 2, 1 simply creates a 1×2 graph and waits for the next plotting command. So the first graph is empty because we chose location 1 here. So it will create an empty location and it will wait for the next plotting command. Subplot by itself does not generate any plot, so it doesn't plot anything for you, so it has to be used along with a plotting function, for example plot in this case. So here we're typing plot tf, so we're plotting f of t. So remember, you always put the independent variable first, t, and then f of t itself. And f of t in MATLAB is simply f. In each subplot or in each graph, remember you always keep r and c constant. So the grid is always a 1×2 for this particular example or graph. since 1 by 2 grid, if you multiply 1 times 2, you have 2. So we have a location for 2 graphs only. So we need to say subplot 1 to 1, location 1, and then subplot 1 to 2. So remember, n, or the last argument here, is the location, and you only change the location each time you use subplot for one figure window. Okay. Now, in the next figure, or in the next location actually, in location 2, we're plotting y of t, and we're adding a title for y of t, plot, x labels, y labels, and so on. And this is the result, the final result for this code. Notice that f of t is drawn or plotted in the first location. Y of t is drawn in the second location, in location 2. In this subplot, R and C are 1 and 2. So we have a grid of 1 row, 2 columns. And in the first location, we're outputting f of t, or plotting f of t. And in the second location, we're plotting y of t. In MATLAB, there is a built-in help feature that will help you further understand how a function can be used and what its purpose is. To access the help feature, you can simply type help followed by the function name that you want to learn more about. Another way to use the help feature is to click on resources and then help. If you type code in the command window, you'll simply see the results immediately outputted in the command window, or if you're storing variables somewhere, you'll see them in the workspace. However, if you're interested in saving your work for further editing later on, or for sharing it, or for submitting it as an assignment, for example, it is important that you create a script file first, and to do that, you'll need to click New Script or go to New Script. Notice that the extension for a MATLAB script file is M, so the script file format is .m. To execute the code written in a MATLAB script file, you will need to click the Run button that's located under the Editor tab. Running a file for the first time will prompt you to save it, or you can alternatively click on the Save icon. Names for files in MATLAB has restricted rules that apply to MATLAB variables as well. So it has to start with a letter, and it may contain numbers and or underscores. Now we're going to discuss some other important commands in MATLAB, including CLC, clear all, close all, and how to add a comment in MATLAB. It's important that you start any script file in MATLAB with the commands CLC, clear all, and close all. The CLC will clear the command window. This will ensure that you're starting with a clear command window, so anything you see in the command window corresponds to the script file itself, nothing else. The command clear all will clear any existing variables that are stored in the workspace. So ensure that you start fresh and that you're not going to use anything that's created previously. And anything that you're using in the code actually is initialized within the code, or it's built in within MATLAB. Finally, the command close all will close any currently opened figures. This way your work will be organized, so you don't have to worry about closing the command windows that were or the figure windows that were open from the previous run of your script file, especially if you have, say, for example, 10 figures and so on. Finally, the percentage sign in MATLAB is used to add a comment. So anything in green here, or anything that follows the percentage sign, is considered a comment in MATLAB. Here we have an example in which a comment is useful. We have a variable named W, which is short for weight, and we're explaining in the comment that W is actually the weight in kilogram, not in pounds, for example, and so on. And H is the height in meters, not in feet, for example. So here a comment was useful, and it's very straightforward, and you don't have to explain it as code instead. This is the end of this video. Thank you for watching. If you have any questions, please post them in the forum. If you have anything that's not related to the lab materials itself, you can email me at alat@auk.edu.kw.